Namaste, welcome back to the Pragna channel. You are watching Machine Learning Basics Theory playlist. And in the last two videos, we have learned about standard recurrent neural networks. Then we learned about LSTM, RNN. And today, or in this video, we are going to learn about GRU neural networks or recurrent neural network. GRU, gated recurrent unit. And we have discussed in the RNN that we use GRU and LSTM in some places where RNN cannot be used. What is gated recurrent unit? GRUs are a type of RNN, which we already know, designed to solve the same problem as long short-term memory networks, particularly the vanishing gradient problem that affects the ability of standard RNNs to learn long-term dependencies. You might be asking, then if it does exactly same as LSTM, why do you need this? Well, GRUs were introduced as a simpler alternative to LSTM with fewer parameters and a streamlined architecture. I guess now you know why. So how GRU work? Well, GRUs have two main gates that control the flow of information. One, reset gate, and another one, update gate. Reset gate determines how much of the previous information should be forgotten. When the reset gate is close to 0, the unit effectively resets, forgetting the previous hidden state. And the update gate decides how much of the previous hidden state should be carried forward to the next time step. It controls the amount of information that is passed on to the next step. When the update gate is close to 1, the hidden state is mostly carried forward. When it's close to 0, the hidden state is updated with the current input. So the GRU combines these gates into a single unit, simplifying the architecture compared to LSTMs, which have three gates. Remember them: input, output, and forget. So this is how the architecture of these three gates looks like. Reset gate, which you can see here, controls the extent to which the previous state contributes to the current state, and update gate determines how much of the previous information is passed to the current state. And hidden state, the internal memory that GRUs update and carry forward through the sequence. So what are the advantages? As we already discussed, it has simpler architecture. GRUs have fewer gates and parameters than LSTMs, making them computationally more effective. And due to the reduced complexity, GRUs can often train faster and require less data to achieve comparable performance to LSTMs. And despite their simpler structure, GRUs often perform similarly to LSTMs on many tasks, making them a strong alternative. And the examples will look similar. Time series prediction, forecasting electricity demand. This is the example or scenario we are going to use later on in the step-by-step explanation. GRUs can be trained on historical electricity usage data to predict future demand. The reset and update gates allow the GRU to retain important trends from past data while updating to new patterns. And the outcome would be energy companies can use GRUs to optimize electricity generation and distribution, reducing costs and improving efficiency. And then in NLP, like machine translation, example English to French, GRUs are used in sequence to sequence models where the input is processed word by word and the GRU's hidden state carries the context forward to generate the translation in the target language. GRUs are applied in real-time language translation apps and services where quick and accurate translations are necessary. And speech recognition, converting spoken language into text. In speech recognition, GRUs process sequence of audio signals, converting them into a sequence of phonetic representation, which are then mapped to text, similar to LSTMs. The GRU's ability to manage sequences helps in recognizing words in a continuous stream of speech. It can be used in voice-activated assistants like Google Assistant or Alexa, which rely on GRUs for recognizing and transcribing speech in real time. And anomaly detection in financial transactions, detecting fraudulent transactions. GRUs can be trained on sequences of transaction data to detect anomalies that could indicate fraud. The model learns to recognize normal patterns of behavior and flags deviations. Outcome or use cases would be banks and financial institutions use GRUs for real-time fraud detection in credit card transactions, protecting customers from unauthorized activities. Okay, so I also said I am going to show you GRU versus LSTM because both are interchangeable. One is simpler and another one is complex. As here it says, simpler architecture with fewer parameters to optimize, more complex with additional gates. And performance-wise, GRUs often perform similarly to LSTMs, but may require less computational power and memory, making them more efficient in some scenarios. And use cases and LSTMs, if you see here, typically perform well, especially in tasks requiring long-term dependencies, but they will be, of course, going to be resource intensive. Both are used in similar applications such as time series forecasting, natural language processing, and sequence prediction tasks. I guess it depends on if you want to handle or pass more parameters to optimize your model or not. All right, it's time for the step-by-step scenario-based explanation. And our objective is to predict future electricity demand based on historical data. And we are going to use past electricity consumption data to forecast the demand for the next hour, day, or week. And as you can see here, historical electricity consumption data, hourly electricity demand in kilowatts. And you can see it is hour 0, 0, 1, 2, 3, and so on and so forth, 24 hours data. And what is the first step? Prepare data set. Okay, so this is not a text, so you are not going to tokenize here. So instead, you have numbers. Whenever you have number, what do? You will normalize. What do you mean? You will scale the data to a range, example 0 to 1, to improve model performance. So how will you normalize something? There is a formula. So x normalize something which is equal to x minus x min divided by x max minus x min. This is what you will use, and you have guessed it. After normalization, our data looks something like this. So you got the max, sorry, x with the current value, let's say 450 minus minimum, let's say 430, which will be 20 divided by, if you say 510 minus 430, 80. So something like that. I mean, these are not all the values, but I'm just saying that's how you will get the normalized value for that x. And this is what our data looks like after normalization. Okay, now you did it, which means we got the input sequences of our past consumption data to predict the future demand, and our values are 0.36, 0.42, 0.31. These are for the past 3 hours, and based on that it has to predict our fourth, which is not shown here, but it is 0.45, which is our fourth hour's demand. It should predict that for me. And our time step process, if you look at it, this is my time step, and my input sequence is this, and it should output this one. And time steps 2, if I give my uh, second, third, and the fourth, it should predict the fifth hour, so on and so forth. So first step, I prepared the data set. Second step is building the GRU model. And here you have again input layer and GRU layers, and then your output layer. Input layer receives the input sequence of normalized electricity demand, and GRU layer processes each step, which you can see here, in the sequence, updating the hidden state with each new input. And the output layer produces the predicted electricity demand for the next hour. And as you can see here, step 1 processes the first time step, which is the 0.36, then it will update the hidden state. Step 2 processes the second time step, which is the 0.2, and it will update the hidden state, so on and so forth. And that you can see here. Okay, so my first hour, second hour, third hour, then it is going to predict my fourth hour. And then as usual, this is forward propagation and backward propagation, if there is anything error. And forecasting future demand using the trained model. Of course, you can input any data you want. The next 3 hours you can, and it will predict the next hour's data. So building, training, that is the training part. I forgot to write it here. And then evaluating. Okay. So you have evaluating test data by two methods. Since you have metrics or numbers here, you will have two methods to do that instead of qualitative like previously. Here you will use something called MAE, mean absolute error. This is the average of absolute differences between predicted and actual values. Then you have root mean square error. This is like the square root of the average squared differences between predicted and actual values. And as you can see, those are shown here. This is the actual demand and this is the predicted demand and this is the absolute error which we are talking about here. Now, similar to our previous scenarios, if you have to plot your accuracy loss accuracy and the loss over time, you can see the improvement in accuracy as the model trains over more epochs, indicating that the GRU is learning to better predict electricity demand. And the loss over time illustrates the decrease in loss during training, showing that the model is reducing its prediction error over time. So in summary, GRUs are powerful for forecasting tasks that involve sequential data like electricity demand. The ability of GRUs to capture short and medium term dependencies makes them effective for this type of time series prediction, and visualization of training metrics helps assess the model's learning process and effectiveness. So to put it, for short and medium term, go with GRU, and for long term, then you will go with LSTM. So that's about these three RNNs. We have standard RNN, then we have LSTM, then you have GRU. So if somebody asks, at least now you know what is the difference between these three and when you will use these three and how do you implement these three. I hope it was helpful. If so, don't forget to subscribe, like, comment, and thank you for spending your time here. See you in the next video. Have a great day. Peace out.